5 minutes isn't really enough time to understand this story properly, but let's start anyway. Because what James Webb actually detected coming from beyond our solar system is not a radio signal, not a beam, not anything transmitted on purpose at all. It's something considerably stranger, a faint chemical fingerprint hidden inside starlight that here on Earth is only ever reliably produced by living things. And the real story behind that fingerprint has more genuine twists, walkbacks, and independent double-checking than most headlines about it ever bothered to mention. Before we get into what was actually found, it helps to understand the tool that made this entire debate possible in the first place. The James Webb Space Telescope launched in December 2021 and now sits roughly 1.5 million kilometers from Earth, orbiting a stable gravitational location called the second Lagrange point. Webb is primarily an infrared telescope built to detect faint heat signatures and stretched out light from extremely distant objects, which also happens to make it exceptionally good at an entirely different job, studying the atmospheres of planets orbiting other stars. When a planet passes directly in front of its host star from our point of view, a moment astronomers call a transit, a small fraction of that starlight passes straight through the planet's atmosphere on its way to Earth. As it does, different gases absorb very specific, precise wavelengths, carving tiny dips into the overall spectrum of light Webb eventually receives. By measuring exactly where those dips appear and how deep they are, scientists can work out which molecules exist in a distant planet's atmosphere, and roughly in what quantities, entirely without ever sending a spacecraft anywhere near it. This technique, called transmission spectroscopy, is exactly how every result in this story was actually obtained, and it's worth keeping in mind throughout, because it shapes exactly what kind of evidence we're really talking about. Let's start with where this signal is actually coming from. The planet at the center of this story is K2-18b, sitting roughly 124 light-years away in the constellation Leo, orbiting a small, cool, quiet red dwarf star once every 33 days. Despite that short orbit, K2-18b sits comfortably inside its star's habitable zone, since red dwarf stars run so much cooler and dimmer than our Sun. In size, it's considerably larger than Earth, roughly 2.6 times Earth's radius and about 8.6 times its mass, placing it in a category of planet we have no direct example of anywhere in our own solar system. A sub-Neptune, somewhere between rocky Earth and the much larger ice giant Neptune. Early observations in 2019, combining Hubble with other instruments, hinted at water vapor in K2-18b's atmosphere, sparking early excitement. More careful follow-up analysis later called that detection into question, suggesting it may actually have been methane. It was an early preview of a pattern that would define this planet's entire story. Bold announcement followed by careful, patient double-checking. Then, in 2023, Webb turned its instruments toward K2-18b and delivered a far clearer picture, confirming methane and carbon dioxide in the atmosphere while finding a notable absence of ammonia. That specific combination matters because it matches a theoretical model proposed by Cambridge astrophysicist Niku Madhusudan, describing a Hycean world, short for hydrogen and ocean. A planet with a thick, hydrogen-rich atmosphere sitting above a deep, planet-wide liquid water ocean. Low ammonia fits this. Picture neatly, since ammonia dissolves easily into water, meaning a large hidden ocean could be quietly absorbing it. This 2023 result alone was already significant, marking the first confident detection of carbon-based molecules in a habitable zone exoplanet's atmosphere. But the moment that actually launched K2-18b into global headlines came in April 2025, when Madhusudan's team, using Webb's mid-infrared instrument MIRI, announced a detection of chemical fingerprints matching dimethyl sulfide, DMS, or a closely related molecule called dimethyl disulfide, DMDS. Here's why that caused such a stir. On Earth, these molecules are produced almost exclusively by living organisms, primarily marine phytoplankton and certain algae. There's no well-established non-biological process that reliably produces them in significant quantities. A Cambridge press release at the time described it as the strongest evidence yet that life might exist on a planet beyond our solar system. Headlines ran with it immediately. And this is exactly the part most headline-driven coverage conveniently leaves out. The scientific community's response was immediate, cautious, and in places openly skeptical. Within days, Oxford astrophysicist Jake Taylor ran his own independent reanalysis of the same raw data and found no statistically significant evidence supporting the DMS or DMDS detection at all. He wasn't alone. Over the following months, multiple independent teams, including researchers Luis Wellbanks, Raphael Luque, and others, ran their own separate analyses using different modeling approaches and different underlying assumptions. Several reached the same conclusion Taylor had. The signal sat right at the edge of the instrument's noise floor, statistically indistinguishable from randomness rather than a confident detection of any specific molecule. One particularly thorough follow-up expanded the search dramatically, testing the observed spectrum against a library of hundreds of candidate molecules individually rather than focusing narrowly on DMS and DMDS, and using multiple independently built analysis codes running on the same underlying dataset to check the robustness of the original claim from several different technical angles at once. A separate detailed study dug into an important secondary question: why different research groups kept getting different answers from the exact same underlying data. It found the apparent signal appeared to be an artifact of a specific technical choice in how the raw data was grouped for analysis, a process called binning. Testing many reasonable binning configurations, researchers found only a small fraction, roughly 1 in 8, actually produced results supporting a detection at all. The same study found that entirely different molecules, including ethylene and chloroethane, fit the data at least as well, sometimes better, meaning even if the signal is real, it currently can't be confidently attributed to any single molecule. In July 2025, a NASA-led study added another layer, comparing conclusions across multiple research groups to determine which findings held up regardless of method. The result was a genuinely nuanced picture, strong confidence across nearly every method tested that K2-18b really does have a water-rich atmosphere, potentially up to half water by mass, with confirmed methane and carbon dioxide, but no conclusive evidence for DMS specifically, tempering without completely erasing the excitement of April 2025. So where does that leave things? As of the most recent, most carefully checked analysis, K2-18b almost certainly has a genuinely remarkable water-rich atmosphere consistent with Madhusudan's Hycean world hypothesis. But the specific, headline-grabbing DMS detection doesn't currently meet the rigorous statistical standard the scientific community requires before confidently announcing a biosignature. It's worth understanding what that standard actually looks like, because it comes up constantly in stories like this one and explains why the debate has dragged on so long. A detection described as 3 sigma corresponds to roughly a 1 in a few hundred chance the pattern is random noise, which sounds convincing but usually isn't treated as sufficient on its own by the standards physicists and astronomers hold themselves to. Major discoveries, including the 2012 confirmation of the Higgs boson, weren't announced until reaching 5 sigma confidence, closer to a 1 in a few million chance of a fluke. The original April 2025 announcement sat right around 3 sigma, explaining both why the team felt confident enough to publish and why so many other researchers immediately treated it as intriguing but unsettled, requiring exactly the kind of independent verification that followed. This entire episode is genuinely a case study in how careful science works. A bold, exciting claim based on real data. Independent. Researchers immediately rechecking it using different methods. Some agreeing, some disagreeing, everyone publishing their reasoning openly so the rest of the field, and eventually the public, can follow exactly how each conclusion was reached. Researchers involved have pointed out this closely echoes 2 earlier cases in astrobiology's history. In 2020, a team announced possible phosphine gas in Venus's thick clouds, initially framed as a potential sign of microbial life, before follow-up studies identified plausible, non-biological explanations, including instrumental artifacts and alternative sulfur-based chemistry that didn't require biology at all. And decades earlier, in 1996, a team announced apparent fossilized microbial structures inside a meteorite that had originated from Mars, a claim significant enough to prompt public remarks from the sitting president of the United States, before careful follow-up research eventually showed the same mineral. Structures could form through entirely ordinary non-biological geological processes. Now, the other half of this headline, the part about a signal. What Webb detected on K2-18b was never a transmitted signal in the way most people picture the word. It's a spectroscopic signature, a chemical fingerprint read out of filtered starlight, fundamentally different from an intentional broadcast, no matter how often. That distinction gets blurred in online coverage. And in fact, in early 2026, a completely separate research team led by C.D. Tremblay directly tested that exact question, conducting a Technosignature search using 2 of the most powerful radio arrays on Earth, the Carl G. Jansky Very Large Array in New Mexico and the Meerkat Array in South Africa. Observing across frequencies, from 544 MHz to 9.8 GHz, a notably wider range than most previous searches of this kind, and covering at least one complete 33-day orbit of the planet, the team processed more than 20 million individual radio detections, filtering for signals showing the specific Doppler shift. A genuine transmission from an orbiting planet should display over time, similar to how the pitch of a passing ambulance siren changes as it moves toward and then away from you. After applying that filtering, published in the Astronomical Journal in March 2026, the team found no signals consistent with an artificial origin anywhere in the K2-18 system. As Tremblay was careful to clarify afterward in comments to the press, this doesn't prove no technosignature exists there, only that this particular, extremely thorough search didn't find one this time. So, to be completely clear, no radio signal, no intentional transmission, and no confirmed evidence of extraterrestrial intelligence has ever come from K2-18b. What has genuinely been confirmed by multiple independent teams using different methods is a water-rich atmosphere containing methane and carbon dioxide on a planet sitting comfortably in its star's habitable zone. Whether that same atmosphere also contains DMS remains a genuinely open, actively contested question. One scientists say will likely require years of additional observation, possibly an entirely new generation of telescopes, like NASA's proposed Habitable Worlds Observatory, still years from launch and not expected to gather meaningful data until sometime in the 2030s at the earliest, to finally resolve with real confidence. It's also worth remembering that even a fully confirmed DMS detection wouldn't count as absolute proof of life on its own. Scientists would still need to rule out every plausible non-biological explanation first, a process that could easily take years of additional observing time, laboratory experiments here on Earth, and careful theoretical modeling before the broader scientific community would be willing to call the case genuinely closed. That's simply how rigorous science works when the cost of getting it wrong, either by claiming too much too soon or dismissing something real out of excessive caution, is this high. If you want more of these patient, fact-checked breakdowns of what Webb is actually finding, rather than the exaggerated version that spreads fastest online, subscribe now, because K2-18b is almost certainly going to stay in the headlines for years to come as more data keeps arriving.